BRDFs can be represented as a set of input values to an analytic equation or as a set of tabulated data that has been captured from real-world objects. Users can adjust parameter values of analytic BRDFs to change the anisotropic highlight on this teapot or the shininess of the handles. Previous methods only enable such real-time edits for simple lighting or without cast shadows. This live screen capture session, we demonstrate our system for editing BRDFs while rendering in real time under a 4000 light approximation of the Galileo HDR probe, including cast shadows. All 4 views of this T-tray scene will be updating as we adjust the values of the parameters to the Ashikman-Shirley BRDF on the teapot and the Cook-Torrance BRDFs on the tray and handles. We begin by adjusting the direction and amount of anisotropy on the teapot. The Ashikman-Shirley model specifies 2 exponents similar to the exponent in Phong, and their values control the shape of the specular highlight. Notice how the complex nature of the illumination in this scene causes the single highlight to resolve into multiple bright streaks as we adjust the value of n sub v. The dark reflection on the spout also becomes more pronounced. Due to the real-time feedback of our system, we can make fine adjustments to the parameter in order to preserve the spout's reflection while keeping the third highlight from resolving. The curves that we have hidden until now are generated by evaluating the BRDF model. We now look at these curves more closely for the Cook-Torrance BRDF of the handles. This one is a function that varies with the theta half parameterization as determined by the sigma parameter that specifies surface roughness. This one is a function of the theta difference parameterization, computed using the Fresnel equation, which takes the index of refraction as one of its inputs. Notice how the handle's appearance changes as we adjust sigma to create a sharper specular highlight. Despite the model being completely colorless, the handles now appear golden instead of silver because the environment contributes to the color as it interacts with the BRDF. This same phenomena can be seen more clearly on the teapot if we remove the blue diffuse term. We will now make the golden teapot silver by compensating for the color of the environment. Even this simple color adjustment was not previously possible when taking complex illumination and shadows into account. Another attempt to offset the color may have been to choose different values for the exponent in red, green, and blue. As we can see by exploring this option, the resulting appearance is quite different. Finally, we will increase the shininess of the tray by adjusting sigma. The different views reveal the view-dependent nature of the specular component, as well as the dependence on the complex lighting environment. Specifically, notice how the overhead camera shows more light reflected towards that view. As sigma is pushed further, the diffuse shadow becomes less pronounced, and a dark reflection appears. Now demonstrate the use of our system with measured factored BRDFs. We begin with the earrings scene where the cloth, posts, and pearls all use white diffuse BRDFs. We load a red velvet as factored by McCool et al. For the cloth, and metallic gold and pearl paint from the Matusik database for the posts and pearls respectively. Unfortunately, real pearl was not in the database, and pearl paint doesn't actually look like real pearl. One problem is that real pearls have much sharper reflections, which we fix by narrowing the specular peak on the left. We are editing the theta half distribution, which controls specular behavior. The factorization used for the Matusik materials is half diff plus a constant diffuse color. We notice that we've lost the hazy quality of pearls due to their secondary reflection, which we fix by bringing in and amplifying the small secondary peak of the pearl paint. The 2 brightest areas of light in this environment, Gray's Cathedral, are the orange doorway and the blue windows seen in the pearl's reflection. Rings are created due to the interaction between the second specular peak and these bright regions of the environment. We choose their exact width and location so they blend together as desired. Now edit the cloth artistically using trial and error. We are editing the P term of McCool et al.'s homomorphic factorization, which controls the behavior along the theta in and theta out directions. Using the same function for both parameterizations ensures reciprocity is maintained. Add a peak and a depression which can be visualized in all 4 views. Fine-tuning their position gives us the exact appearance we want. Notice that all 4 views use the same BRDF as defined by these curves, and our edits, while artistic, cannot be applied consistently using 2D image editing.